Okay, so what we wanted to look at was permutations of objects where some of the objects are alike. Remember what a permutation is? A permutation is an ordered arrangement, right? Is an ordered arrangement. But if you have objects where some of them are alike, say if I have, let's say, 5 objects where 2 of them are alike and 3 of them are alike, right? The number of permutations of that will not be 5 factorial anymore, right? Because when you interchange the same objects among themselves, you don't get a different arrangement anymore. Is everybody clear? Okay, so remember okay, so remember we were looking at the example of 3 objects. So let's say A, B, and B. Now, assuming that these 3 objects are distinct, right? How many permutations do I have? 3 factorial permutations, right? Assuming these 3 objects are distinct, right? And so what are those, but the problem here is when you interchange B and B, you don't get a new permutation, right? Is everybody clear on that? So how am I going to count then? Well, let me write down the permutations of A, B, B. So this would be, another one would be B, A, B, and another one would be B, B, A, right? And it seems like there are only 3 permutations, right? There are only 3 permutations of the 3 objects that I have where 2 of them are the same. But if I assume that they are all distinct then, right, how many permutations do I have? For now, let's say, think of one of them as B prime, right? So if they were all distinct, then what are the permutations? What would be the permutations if they were all distinct? So obviously I'm going to have A, B, B prime, A, B prime, B, right? I can also have B, A, B prime, A, B, right? I can also have B, B prime, A, and B prime, B, A, right? Is that making sense? If for a second I'm thinking that the 2 B's that I have, let's label one of them as B prime, and then if you think of them as just distinct objects, then there are 6 or 3 factorial permutations, right? Now if I think of B and B prime as the same, then I have only 3 permutations, right? So if you think about it, so let's look at the distinct one, right? For each distinct permutation that I have, right? Each distinct permutation is associated with 2 permutations if all the objects were distinct. each distinct permutation is associated with two permutations if the objects were distinct, right? So how am I getting 3 out of 6? Well, there are 3 factorial permutations here, right? Okay. And if you think about the b's, how many ways can I permute the b's among themselves? Just the b's. So if you pick one of the 3 permutations, how many ways can you permute just the b's among themselves? 2 ways, right? Or 2 factorial ways. You guys get that? If I pick one of the 3 permutations on the left, right? How many ways can I permute or the b's among themselves? Well, there are 2 positions for the 2 b's, right? So I can permute them in 2 or 2 factorial ways. So basically, if I divide 3 factorial by 2 factorial, that's exactly what I'm getting. That's 3. Is that making sense? So once again, look at the three distinct permutations of the 3 objects A, B, and B. Now, if the B's were distinct, right, then I have 6 permutations. So notice that for each distinct permutations, there are 2 permutations if we think of the B's as distinct, right? So that's why if I divide 3 factorial is the number of permutations assuming they were distinct. If I divide that by 2 factorial, I'm going to get the actual number of permutations. Is that making sense? So let's now think about the letters that I have. P, E, P, P, E, R. P, E, P, P, E, R. So we want to know how many permutations do these letters have, right? Well, so I'm going to say let X be the number of distinct permutations of the letters in pepper. Okay, so X is the number of distinct permutations. That's what I want to find. I want to find X. Okay. Now we are going to count the number of permutations of pepper, assuming all the letters are different. All the objects are different in 2 different ways. So count the number of permutations of the letters in pepper in 2 ways. Number of permutations. Sorry, I have to say one more thing. Of pepper, assuming the letters were distinct in 2 ways. In 2 ways. Well, what are the two ways? Okay, I want to count the number of permutations of the letters in pepper in two ways. So here are the two ways. First of all, if they are distinct, what's the number of permutations? How many letters do I have there? There are 6 of them, so the answer is 6 factorial. There are 6 factorial permutations. Now, I'm going to count that in a different way. Look at the distinct permutations of pepper. Like there are X of them. I assume there are X distinct permutations of pepper. Pick one of them, right? For each one of them, right? How many ways can you permute the E's among themselves, and how many ways can you permute the P's among themselves? Is that making sense? So for each distinct permutation, how many ways can you exchange the E's among themselves, and how many ways can you exchange the P's among themselves? Can somebody answer that? Yeah, I can exchange the E's among themselves in 2 factorial ways, and I can exchange the P's among themselves in 3 factorial ways. Does everybody see that? Right? For the P's, I have 3 positions, right? So you can permute the 3 P's among themselves in 3 factorial ways, right? Because 3 factorial is the number of permutations of 3 objects, right? Am I making sense? So for each distinct, for each, maybe I'll write it down here. For each distinct permutation of the letters in pepper, we can exchange the E's among just themselves in 2 factorial ways, and the P's and the P's among just themselves in 3 factorial ways. So number of permutations of the letters in pepper, if the letters were distinct, is also equal to x times 3 factorial times 2 factorial. Let's see if you agree with that. There are x distinct permutations, and for each one there are 3 factorial times 2 factorial ways you can rearrange the p's and e's among themselves, right? Is that making sense? So therefore, x times that would be the total number of permutations if they were distinct. Well, that's supposed to be the same as 6 factorial then. Well, then I can solve for x and say that x is 6 factorial divided by 3 factorial times 2 factorial. Is that making sense? So what am I getting the answer to be? What I'm getting the answer to be is that I have 6 objects, 2 of them are alike, 3 of them are alike, right? Well, then the number of permutations is 6 factorial, that's the total, 6 is coming from the total number of objects, 3 factorial in the denominator coming from the fact that 3 of them are alike, 2 factorial in the denominator is coming from the fact that 2 of them are alike. You see the pattern? And that pattern persists in general. So in general, if you have n objects where n1 of the objects are alike, n2 of them are alike, nk of them are alike, then the number of permutations of the n objects will be given by n factorial divided by n1 factorial and 2 factorial nk factorial. Is everybody okay? If the objects were distinct, then you only get n factorial, but because you have n1 of them are the same, and 2 of them are the same, and k of them are the same, you have to divide by n1 factorial and 2 factorial and k factorial. Is that making sense? Okay. Let me know if you're done writing it down, and we're going to do some examples. Okay, so let's do this example here. It's a chess tournament that has 10 competitors, of which 4 are Russian, 3 are from USA, 2 are from Great Britain, and 1 is from Brazil. If the tournament result lists just the nationalities of the players in the order in which they placed, assuming no tie, how many outcomes are possible? There are 10 players, so you're ranking them from 1 to 10, right? 10 players, you're ranking them from 1 to 10, but when you are, instead of listing each player's name, you're listing their nationalities. So the first place, so let's think about how one of the results may look like. One of the results may look like, first place, United States, okay? Second place, let's say Russia. How many USA? 3. So let's say another USA, let's say in Brazil, okay? And then B for Brazil. I'm going to use G for Great Britain, okay? So this would be G, and then I have more Russians, USA. Do I have 10 of them? I guess I need one more, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, 4 of them are Russians, 3 USA, right? I have 3 of them, and then 1 Brazil and 2 Great Britain, right? So one of the possible outcomes will be this, right? Is everybody clear? Once again, you are ranking 10 players. Instead of writing their names, you are writing their nationalities in order. Okay. All right. So how many possible outcomes are there? How many possible outcomes can I write down? Anybody? That doesn't make sense to me. What you have to say is say it in terms of factorial, then it's going to make sense to me. Why are you saying that? So you're basically okay. So you're basically trying to say is that whatever the answer is the same as saying the answer is the same as the number of permutations of 10 objects where 4 of them are alike, 3 of them are alike, 2 of them are alike, right? You're essentially saying that, right? Does everyone get that? Because you have the letters U, R, B, and G, right? And you have 3 U's, 4 R's, 2 G's, and 1 B, right? You are taking the permutations of these letters, right? So there are 10 of them, 4 of them are alike, 3 of them are alike, 2 of them are alike. So it's basically the number of permutations. So the answer is the same as answer is the same as the number of permutations of 10 objects where 4 are alike, 3 are alike, and 2 are alike. Okay, so the answer is so the answer would be 10 factorial divided by 4 factorial, 3 factorial, 2 factorial. You can put 1 factorial if you want to. There is 1 Brazilian player. Did that make sense to you? Does everybody agree that that question, the answer for that question is the same as the number of permutations of 10 objects having 3 alike, 4 alike, and 2 alike? Right? Okay, let's do another one. How many different signals, each consisting of 9 flags hung in a line, can be made from a set of 4 white flags, 3 red flags, and 2 blue flags if all flags of the same color are identical? How many different signals, each consisting of 9 flags, hung in a line, can be made from a set of 4 white flags, 3 red flags, and 2 blue flags? if all flags of the same color are identical. So what should be the answer? Like one possible signal may look like what? One possible signal may look like you have red, 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 white, 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 blue, blue, right? One possible signal is that. Is everybody okay with that? Okay, so what's the answer? Somebody who plays soccer. Can you answer that?
Is it 9 factorial over 4 factorial times 3 factorial times 3?
Yeah. Does everybody agree with that? So the answer is 9 factorial. So this is basically the same as the number of permutations of 9 flags, where 3 of them are alike, 4 of them are alike, and 2 of them are alike. So you divide that by 4 factorial, 3 factorial, and 2 factorial. Is everybody okay? I saw the soccer players going into the gym after playing, right, in the rain. You guys played in the rain, right? Yeah. Long time ago when I was in probably high school, we had like 20 minutes of break and we played soccer in the rain. And we had a dress code of white color. So I had mud all over me and I went to the class after that. And the teacher wasn't happy about it at all. So okay, so here is another example. Oh no, this is not an example. Sorry, this should have said a definition. Okay. So a permutation of n objects taken k at a time. A permutation of n objects taken k at a time is defined to be an ordered arrangement of k of the objects. Okay? A permutation of n objects taken k at a time is defined to be an ordered arrangement of k of the objects. Let me give you an example. Suppose I have 3 objects, A, B, and C. Now, I am not arranging all of them. Okay, so what I'm doing is I'm picking 2 at a time and arranging them. Am I making sense? Take 2 at a time and look at possible arrangements of the 2. So, what are the possibilities then? If I take 2 at a time, then I'll be getting the arrangements what? If I take A and B, I get AB or BA, right? Those are the possible arrangements. If I pick A and C, then I get possible arrangements AC and CA. If I take B and C, then I get possible arrangements BC and CB, right? Is that making sense? So the number of permutations of 3 objects taken 2 at a time is 6. Do you get that? The number of permutations of 3 objects taken 2 at a time would be 6. Is everybody okay? You have 3 objects, take 2 at a time, look at the number of permutations of the 2. Take another pair of 2 objects and do the same thing. Are we okay with that? Okay, so I'm going to use the notation P and K. So K is the subscript there, N is the superscript there. So P and K will denote the number of permutations of N objects taken K at a time. Number of permutations of N objects taken K at a time. My claim here is that P and K is N factorial divided by N minus K factorial. Okay? And we're going to justify that claim in a bit. For now, take it as a fact. So if I use that as a fact, then for example, what's the number of permutations of 3 objects taken 2 at a time from that formula? Well, from that formula, N is now 3, K is 2. So I get 3 factorial over 3 minus 2 factorial. And if you do the arithmetic, you get 6. Okay, if you do the arithmetic, you get 6. I hate when people say, if you do the math, you get 6. No, you're doing arithmetic. If you do the arithmetic, you get 6. Okay. Is arithmetic math? No. Okay, so for example, P32 would be 6, and we did that explicitly by writing out the permutations in red. Okay, so let's look at the number of permutations of I have already showed you the number of permutations of A, B, and C taken 2 at a time. There are 6 of them. That's what I have in my table. What I want to do now is justify that claim, right? So we were looking at the number of permutations of N objects taken K at a time. So how do I justify that? So notice that we have 1, 2, 3, ... So basically, this is the first position, this is the second position, and this is the kth position, because we are picking K objects at a time out of the, but I have N of them. Okay, K is smaller than N. So I'm taking K at a time, and then I'm looking at the number of arrangements, right? So I have N objects. For the first position, how many choices do I have? How many choices do I have for the first position? Well, there are N objects that I'm picking from, so there are N possibilities for the first object. And once I picked an object for the first position, there are only N minus 1 choices left for the second, N minus 2 choices left for the third, ... Now somebody tell me, how many choices do I have for the kth position? How many choices do I have for the kth position? Look at the pattern and see what I should be writing on the kth position. N minus 1? No. That's 1, right? N minus 1, that's 1. That's when I have, remember, that's when I'm looking at the number of permutations of all N objects. I take an N at a time. N minus K close. What's that? Say it again. N minus K plus 1, very good. Remember, the first position, the number of choices is N minus 0. Second position, the number of choices is N minus 1. Third position, the number of choices is N minus 2. So you're from N, you're subtracting 1 less than the position number, right? From n, you're subtracting 1 less than the position number. So for the kth position, from n, you'll be subtracting 1 less than the position number k, which in fact is the same as n minus k plus 1, as you said, okay? Alright, so that's it. So then the number of, so p and k, the number of permutations of n objects taken k at a time will be n times n minus 1 times n minus 2 dot 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 n minus k minus 1, right? Does that look like my claim? Oops, not yet. Okay. It doesn't look like my claim, so what should I do? Well, what we're going to do now here is that I am going to make this quantity, force this quantity to be n factorial. This is not n factorial right now, right? To get n factorial, I have to multiply all the numbers from 1 up to n, right? So what numbers are missing? So if I want to make this n factorial, what other numbers do I need to put in there? So the last number here is n minus k minus 1, right? But I want to go all the way up to 1, right? So what can I put in there? What would be the next number that I need to put in to get to the 1? N minus k would be the next one, right? Now I subtract 1 more than the previous one. Then I'm going to subtract k plus 1, right? And I keep doing that. So, well, let's write down one more line. So n minus, the next time I'm going to subtract k plus 1, right? K plus 1. And dot 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 all the way until I get 2 and 1, right? Is that making sense? How do you get 1? Well, you subtract n minus 1, right? From n. From n, if you subtract n minus 1, you're going to get 1. So until you get 1, you keep subtracting from n. But as I have done it, I have changed the quantity, right? I don't like that color. So, okay, so now I have to divide by what? I have to divide by n minus k, n minus k plus 1, dot dot dot, 2 times 1, right? Because those factors weren't there, right? So if I am multiplying them, I have to also divide by them. Now, can someone tell me what I have in the numerator then? Remember, the numerator now becomes what? N factorial. What can you say about the denominator? Very good, n minus k factorial. And that better look like my claim, and it does. Okay, so the p and k then is given by that. So the number of permutations of n objects taken k at a time is given by n factorial over n minus k factorial. Is everybody okay with that? Okay, that was it for permutations.